Accelerated Math Analysis. We're continuing on with Lesson 12.1, where we're looking at sequences that are defined recursively. What did that mean? You have to have a start. You have to have a beginning number in your sequence, in your pattern. And then you'll be given a formula that relates to at least one previous term. To find the nth term, you might work with an n-1 term or an n-2 or n-3 term. So you have to go backwards to be able to find your next term. We were almost done. I'm just going to rework here. We found a sub 3 was 27. What we can do immediately is go back to this pattern of a sub n equals n plus 3 times a sub n-1, and we can know that our fourth term, if n is equal to 4, n is 4 right here, plus 3. Well, if n is equal to 4, we know that n-1 is 3. So that's a sub 3. A sub 3 is 27. We saw that just in the last problem. 3 times 27 is actually 81. 81 plus 4 is 85. So even right now, I hope you've gotten the hang of this pattern. One last thing, they want us to go to the fifth term. Following this guideline up here, if n's equal to 5, we'd have 5 for n plus 3 times, well, our a sub n-1. n-1, of course, is a 4. The term before the fifth term is the fourth term. And we just found that to be 85. We just did that a moment ago. And 3 times 85 is 255, you could quickly confirm. And at that point, 5 plus 255 is 260. So recursive formulas can take a while to work out because to get to your current term, you have to at least go one step backwards to the previous term. We're going to see, for example, 6, that we actually have a pattern where we're going to have to work with 2 previous terms. U sub 1 is 1, U sub 2 is 1. But now we'd like to find U sub 3. U sub 3, and again, if we've got this worked out right in here, what you can see is if n is equal to 3, 3 minus 1 is 2, and 3 minus 2 is 1. In other words, to find the third term, add the second and the first term together. Both of those are 1s, and 1 plus 1 is going to get you a 2. If we wanted to find our fourth term using this pattern, well, if n's equal to 4, the term right before that would be the third term. And if we were to go back a term before that, that would be the second term. So to find the fourth term, we need to add the third and the second together. We just saw that the third term was a 2. The second term, they told us right here, is a 1. 2 plus 1 is actually a 3. Now what? Well, let's just go one more. We're supposed to go to our fifth term, U sub 5. U sub 5 would be U sub 4 plus U sub 3. What was U sub 4? You just saw it. You just found that a second ago. That's a 3. And U sub 3, we found that to be a 2. So what is U sub 5? U sub 5 is a 5. This is a very, very, very famous kind of a sequence. It's known as the Fibonacci sequence. We start with a 1, then we go to a 1. 1 plus 1 is a 2. And then we'd add 2 plus 1. Add those 2 previous terms, you'd get a 3. Add 2 plus 3, your next term would be a 5. Add these 2 terms together, 3 plus 5, you'd get an 8. So again, the Fibonacci sequence, a sequence that actually appears very commonly in nature. Let's take a look at our last problems here. We've got a few of them. Write out the sum. First off, it's completely okay to have a zeroth term. This is a sigma right here, this Greek letter. This is the Greek letter sigma. And generally what will happen is you'll have k equals a number up here. This is what you start with, and this is what you end with up on high. So you'll always have that worked out. Now, the sigma means add. So what this really means is plugging a 0 into the formula 2k plus 1. So we'd have 2 times 0 plus 1. And this is like the Greek letter S to us, S for sum. Then we'd let k equal 1. Now, when k is equal to 1, we'd have 2 times 1 plus 1. And then we'd say now put in k equals 2. So we'd have 2 times 2 plus 1. And you get the idea. We'd have k equals 3. Well, that's 2 times 3 plus 1. Here's the problem, though. The ending is unspecified. It's just n minus 1. So that's 2 times n minus 1 plus 1. So what does all this work out to? Well, 2 times 0 is 0, and we'd have a 1 here. And here you could see 2 times 1 is a 2, 2 plus 1 is a 3. Here we'd get 2 times 2 is a 4, 4 plus 1 is 5. Here 2 times 3 is 6, 6 plus 1 is 7. And we're just going to keep going all the way up here. This is 2 times n minus 1. Well, that's 2n minus 2 plus 1. This would go all the way up to 2n minus 1 when we simplify it. So something important for you to see, whenever you have a 2k plus 1, that's an odd number. Remember, 2k would always be even. If you were to ever add 1 or subtract 1, you'd always be generating odd numbers. So this is saying add up a whole bunch of odd numbers, stopping at an unspecified n minus 1 term. And that's what you would see. From here, example 6, what scares kids, definitely. I think they can say, oh my goodness, wow, working this out, we'd get 1 to the third minus 7 times 1 plus 2 to the third minus 7 times 2. And then we'd say plus, and you get the idea. You keep doing this all the way up to the 12th term. That's 12 to the third minus 7 times 12. And my goodness, this could definitely be quite intimidating for kids, understandably so. Tell you what, our calculator can actually help us considerably. Let's see how. If I go to math, press the math button. Thank goodness, down here we have summation for really number 10. And when I hit enter, I'll get that sigma. Now, generally, you could type in whatever variable you'd like. I like to just type in an x. It's the most frequent variable. So I'm going to say x equals 1. That's my lower bound. I'm going to come up here with a 12. And then I just have to type in my formula very nicely in terms of x. And it only takes you a moment to do that. If you would have done all of this with k, you'd get the same answer without hardly any work at all. You have your answer, 5,538. So wonderfully, there are problems on your assignment where you'll be able to work problems out with the calculator in this regard. Finally, let's take a look at number 7. It says, express using sigma. Express using sigma. And there are actually a couple of ways we can do this. You can see we've got 1 plus 3 plus 5 plus 7 plus 23. I think what kids are quickly going to notice is, hey, wait a minute, that looks just like example 5. That looks just like example 5. And, how do we know? Well, we've got all those odd numbers. 1 plus 3 plus 5 plus 7, and we keep going and going and going, and we're going to go all the way up to 23. So, my word, as we try to work this out, you might guess that just like in number 5, we could start with k equaling 0. K equaling 0. Now, the last thing we have to do is find our upper bound. And that can then beg the question, how would we know what k value that is? Well, look, I guess I just want to show you, you could have known that k was equal to 0 just as well, just with the 1. You could have gone 2k plus 1 equals 1. You could have solved that, and you'd have gotten 2k equals 0 and k equaled 0. What if we would have had 2k plus 1 equals 23? Well, we'd minus a 1, and we'd have 2k is equal to 22, leading us to say that k would equal 11. And that's our upper bound. Sure enough, when we plug in 11 into that formula, we end with a 23. So that's it for this section. Our homework is EOO, of course, stands for every other odd. Some of the problems will be nothing more than using a calculator. Very much the problems that you've seen in the notes are reflected in this assignment. Best of luck to you.